Good evening, everyone. I'm Manesh Ambikar, PhD candidate from Aerospace Engineering at C Bengaluru. Welcome to this week's live interaction for the NPTEL course Engineering Mathematics 2. This course is offered by Professor Jitendra Kumar on NPTEL platform. The NPTEL course code is NOC23MA25, and today we'll be discussing few problems and concepts related to the material taught in second week. Primarily in this week, Professor covered Stokes' theorem, initially covered Green's theorem, surface integral, so line and surface integrals, then Stokes' theorem, which is a generalization of Green's theorem in 3D, and then divergence theorem. Okay, we have the first problem here. So problem number one, it states that using Green's theorem, evaluate the line integral circular integral over curve C y dx, where the curve C is given by a cos t of I plus a sin t of j for 0 to 2 for t in 0 to 2 pi. So if I have to draw this, so it will look something like this. This is my x-axis, the other one is my y-axis, this is my origin, and I'll take this length to be a, and my x component is a cos t, and my y component is a sine of t. This is basically equation of circle x square plus y square equaling a square, and t, it is given that t will vary from 0 to 2 pi. So when t is 0, we have x is equal to a, y is equal to 0. So this becomes our starting point for the curve C. It proceeds in an anti-clockwise manner and comes back at t equal to 2 pi. We are asked to evaluate integral over curve C y dx. So we'll be using Green's theorem, which essentially states that for a closed curve C, it basically relates line integral for a closed curve C to the region enclosed by that particular smooth line, smooth closed curve. So you essentially have integral of circular integral over f1 dx plus f2 dy. This is equal to dou f2 by dou y minus, sorry, dou f2 by dou x minus dou f1 by dou y of dx dy. Here we have the requirement that f1 and f2 and f2 are C1 continuous over this particular region D. What this C1 continuity means that essentially both of these functions it means that both of these functions are continuous and differentiable. Their first derivatives should exist and be continuous. C1 is written like this. Okay. This can be again rewritten as circular integral of f dot dr. See, with vector f being the vector field given by f1 I hat plus f2 j hat. In this particular example, we have f1 is equal to y, f1 is equal to y and f2 is equal to 0. Dou f1 by dou y is nothing but 1. Therefore, integral of y dx over curve C is nothing but double integral over the region D enclosed by the curve C to be equal to 0 minus 1 dx dy, which is nothing but minus 1 times integral of dx dy over region D. This is simply the area of region D minus 1 times area of region D. The area of region D with D being the circle, a circle is nothing but pi times r square, which is pi times a square here, since the radius is r. Therefore, integral of y dx is nothing but minus 1 times pi a square. So the first option. I hope this is clear. If there are any doubts, now you can raise any questions if you have any doubts. We'll now move to the second problem. Let C be a square bounded by x equal to 0, x equal to 1, y equal to 0, and y equal to 1. So if I draw it on the xy plane, this is my x-axis, y-axis, origin. This is the line y equal to 0. X-axis itself is the line y equal to 0. Y-axis is the line x equal to 0. Then you have, if I take this as my unit distance, this becomes my square. So this whole region I'll again name as D, and in the anti-clockwise direction, the enclosing curve is C. And we are asked to calculate the value of x minus y dx over plus y minus x dy. So we have to calculate integral over the closed curve C, x minus y dx plus y minus x dy. If we go back to the Green's theorem statements that we have written earlier, this is similar to f1 dx plus f2 dy, which which is our which is this part, which is this part. So in our case, f1 is nothing but x minus y dx, and f2 is y minus x. This is equal to, the first term is dou f2 by dou x, which is nothing but dou of y minus x by dou x minus of, your second term would be, write this arrow, your second term would be minus of dou f1 by dou y, which is partial derivative of x minus y with respect to y into dx dy, which is nothing but partial derivative of y minus x with respect to x is minus 1, minus of partial derivative of x minus y with respect to y is again minus 1, dx dy. So minus 1 plus 1 will cancel out, we'll get 0. 0 times area of D is nothing but 0. So for this particular problem, the line integral across the closed curve C turns out to be 0. This raises an interesting question whether, like in the first week's lectures, we studied what are conservative vector fields. So if I have to write this particular vector, this path integral in terms of vector field, it would be nothing but f is equal to f1 times I plus f2 times j, which is equal to x minus y I hat plus y minus x j hat, right? And if we know that if f is, so if f is a conservative vector field, then path integral over a closed path should be 0. This is what we had studied in previous class, previous week's lectures. Then vanishes. So one can wonder if in our case also vector f is equal to some grad of phi. From this, if you do the calculation and figure out phi, you you basically have dou phi by dou x is equal to x minus y, and dou phi by dou y is equal to y minus x. From this, you can figure out phi as a scalar field over x and y to be x square by 2 minus xy plus y square by 2 plus c. Right, you can quickly verify this, and we see that indeed the vector field f given by f1 I hat plus f2 j hat, which is nothing but x minus y I hat plus y minus x j hat, is a gradient of a scalar field, and therefore even if we take say any other closed path like this, it would still vanish. But to solve this particular problem, we have made use of Green's theorem and not by checking whether it was a conservative vector field or not. Okay, so now we move to the third problem. We are asked to calculate the area of surface cut from the bottom of the paraboloid z equal to x square plus y square by the plane z equal to 3. Draw this as my z axis. That's my x axis. This is my y axis. This is my z axis. So it's paraboloid z equal to x square plus y square. It will pass through origin. You can verify that by simply putting x, y, z to be 0. And suppose this is my point z equal to 3. Then I can have this particular plane like this. And it would cut the surface. It would cut like this. So we are asked to calculate the area of this particular surface. This plane is z equal to 3. So this surface is, so I'll write paraboloid surface is given by the equation f of x, y, z is equal to z minus x square minus y square, which is 0 in this case. So this gives us the equation of paraboloid surface, and we want to see, so we, we then look at the normal to this particular surface at say any other point. This is an oriented surface. So we are looking, it can have both the inward and outward normal. In this particular case, we are looking at the outward normal. So gradient of f is equal to minus 2x I hat minus 2y j hat plus 1 k hat. This is my gradient of f. This whole surface, paraboloid surface, I'm denoting it by sigma, whereas this projection I'm denoting by a. Then the relation between d sigma and dA is given by sigma is nothing but normal grad f dot t upon norm of grad f. Okay. And if I just substitute all the values, I can again rewrite this. This is nothing but actually the cos of this. My p is equal to minus k hat. Okay. And this whole thing is nothing but cos of the angle subtended between the normal vector to the surface and the normal vector to the projection area. So if I just rewrite this, the whole thing is surface area is nothing but integral over surface A norm of grad f upon norm of grad f dot p times dA. In this particular case, norm of grad f is nothing but root of 4x square plus 4y square plus 1. Also the vector p is but minus k hat, or you can take it plus k hat. It won't make much difference since we are anyways taking modulus. If you do grad f dot p, you end up with 0 plus 0 plus minus 1. The norm of grad f by norm of grad f dot p is nothing but root of 4x square plus 4y square plus 1 on 1. So my surface area is nothing but integral over projection area A root of 4 times x square plus y square plus 1 times dx dy. If I look at my projection area A, I can see that it's a circle, yeah, given by the, so for projection area I have to substitute z equal to 3 in f of xyz. So that essentially gives me x square plus y square equal to 3, which is circle with radius 3, root 3, sorry. So I can rewrite my surface area equation in polar coordinates as under root of 1 plus 4 r square r dr d theta, where r is varying from 0 to root 3 and theta is varying from 0 to 2 pi. Let me take, let t square is equal to 1 plus 4 r square. If I differentiate on both sides, I'll get 2t dt to be equal to 8r dr. Therefore, my integral of t times r dr is nothing but t dt by 4 is equal to t cube by t cube by 12 times pt, t cube by 12 plus c, and this will be limited by the values of t. When r is 0, my t is equal to root of 1 plus 4r square is equal to 1, and when r is root 3, then my t is similarly root of 13. So if I substitute this whole thing, so these two things in my surface area formulation here, I essentially end up with integral over 0 to 2 pi root of 4r square plus 1 by 12 whole cube from limits 0 to root 3 d theta, which is nothing but 13 root 13 out of space here. I'll just remove a few of these things. I'll write it on the top. This is continued on the top. So here. So this is nothing but 13 root 13 minus 1 by 12 into integral of d theta over 0 to 2 pi. So into 2 pi, which is pi by 16, 13 root 13 minus 1, which is the first option. Slightly involved, but in terms of computation, but the basic principle is quite simple. You have a level set. In this case, it's a paraboloid with given by this equation f of x y z equal to c. Calculate the gradient. You calculate the normal to the level set given by gradient of normal to surface given by gradient of f, and then you also choose a projection on which you would like to do this to calculate this area. So in our case, we have chosen the projection to be given by the cutting plane itself, which is z equal to 3. This gives us a projection area bounded by the curve x square plus y square equal to 3, which is nothing but the equation of a circle. So this is my projection area, which is a circle with a radius of root 3. Now my ratio of projection area to the ratio of actual surface area is given by the cos of the angle between them, mod of the cos of the angle between them. That essentially is nothing but mod of grad f dot p upon mod of grad f into norm of grad f into norm of p. But since p is an unit vector, this essentially does the function of cos theta or cos gamma, and which is the notation used by professor. And then we just calculate surface area by doing sigma is nothing but integral or 1 by cos of gamma dA over the area. If this is clear and there are no questions on this, we'll move to the next problem. This is the fourth problem, and it states that it rather asks if to calculate the area of surface cut from the nose of paraboloid x equal to 1 minus y square minus z square by the plane x equal to 0. So I'll again draw my 3 axes. This is my x, this is my z. I made a mistake here, so I think this should be x, this should be y, but it won't. This is my x, this is my y, this is my z, and so and my paraboloid it goes like this, and it cuts at x equal to 0. It will be cut by a plane. Give a projection A. If I look it with x-axis on the top, if I look at with the x-axis from the top, it would look something like this parabola going down, and then it's cut by a plane, by the YZ plane, to give a projection. This is my A, this outer is my sigma, and I'm asked to calculate sigma, which is my surface area. A is my projection area. Again, we'll first look at the projection. So it is given by x equal to 0, which means 1 minus y square minus z square equals 0, which is nothing but equation of the circle y square plus square equal to 1. So my projection in the yz plane would be a circle with a unit circle at origin. Next, I look at my set f of x, y, z. That is nothing but x plus y square plus z square minus 1 equaling 0. Okay. Now to calculate the normal, I'll calculate gradient of f, which is nothing but I hat plus 2yj hat plus 2z k hat. And from my projection area, I know that my normal is p hat is equal to I hat along the x-axis. Therefore, my cos of gamma, or rather, the reciprocal of cos of gamma is nothing but mod of grad f upon mod of grad f dot p hat, which is equal to root of 1 plus 4y square plus 4z square upon grad f dot p. If we quickly do here, it's nothing but 1. So my sigma is nothing but root of 1 plus 4 times y square plus z square dA, which is nothing but root of 1 plus 4 times y square plus z square dy dz. If we convert this to polar coordinates, it becomes, so polar coordinates in the yz plane, 1 plus 4r square r dr d theta. R is varying from 0 to 1, theta is varying from 0 to 2 pi. If we substitute it into our, like the formula that we got previously, it is nothing but 1 by 12 root of 1 plus 4r square whole cube rounded over 0 to 1 d theta from 0 to 2 pi, which is nothing but 2 pi by 12 pi root 5 minus 1. So it's basically pi by 6 into 5 root 5 minus 1. This is quite similar to the third problem, but I thought that the overall process is a little involved, so we would go through both the examples. If that is clear, we now move to the fifth problem. The flux of the field F is minus y I hat plus xj hat, and we are asked to calculate flux of this field across the portion of a sphere given by the equation x square plus y square plus z square equal to 9. Sphere, we are actually asked to calculate it only in the first octant. So while my whole sphere would look like this dotted line, we have been asked to restrict ourselves to only the first quadrant. So I look at the level surface for this particular surface, the first octant of this sphere, and it is nothing but x squared plus y squared plus z square minus 9 equaling 0. If I look at the out normal, that is 2x I hat plus 2y j hat plus 2z k hat. So we could, in this question, it is given that we have not to look at the direction away from the origin. So this is the direction that we'll be looking into. There can be both pluses and plus and minus here, but since we have been told away from origin, this will just take the gradient of f itself and not its negative. If I want to look at the outward normal, it becomes grad f upon norm of grad f, which is nothing but 2x I hat plus 2y j hat plus 2z k hat upon root of 4 times x square plus y square plus z square. Since we are restricted to calculate this normal over this particular surface sigma, we know that x square plus y square plus z square for this sigma is nothing but 9. And if we take the square root, we essentially end up with square root of 36, which is 6. If we divide this whole thing by 6, we get 1/3 of xi hat plus yj hat plus zk hat. So this is my outward normal. And if I want to calculate flux, I want to do f dot n d sigma sigma, which is nothing but minus yi hat plus xj hat dot 1/3 of xi hat plus yj hat plus zk hat d sigma. So we can take the 1/3 here minus yx plus xy, no component of k hat in the first term, so 0 d sigma, just to cancel each other out, and therefore we end up with net outward flux being 0. So this particular octant, this would be the flux coming out of like the spherical part, but we also have 3 surfaces. I'll just ABC and O. So this is the flux coming out of ABC. If you look at the flux coming out of say AOC, which would be look like a surface like this on the YZ plane with a radius of 3. You can see that all the field lines will lie in the all the field lines will lie in the XY plane. If we look at the OC, which lies in the XY plane, so the normal to this would lie in the K plane, and my vector fields themselves lie in the XY plane. So f dot n would be 0 again for the surface COB. If we look at the surface AOC, then my f is again minus yi hat plus xj hat, and my surface normal here is I hat minus 1 minus y. So if I want to calculate flux of AOC, it equals integral of minus y d area AOC. If I want to calculate area of AOC, it's nothing but root of minus r cos theta. I need more slides. If I look at the curve AOC or the surface AOC, it would end up to be integral of minus y dA, which is nothing but double integral of minus r cos theta into r dr d theta. R is varying from 0 to 3. Theta is varying from 0 to pi by 2. So it is minus r cubed by 3, and the integral of cos from 0 to 3 and integral of cos theta d theta, which is nothing but minus 9 times sin theta varying from 0 to pi by 2, which equals minus 9. If we take the final surface, it's nothing but COP for this case. Vector n is nothing but, sorry, AOP. We need to take AOP. And A is alongside along x. Here my normal vector would be j hat. Therefore my f dot n would be nothing but x double integral x dA, is nothing but r sine of theta r dr d theta from 0 r varying from 0 to d theta varying from 0 to pi by 2, nothing but r cubed by 3 over 0 to 3 sine theta d theta, which is 9 times minus cos theta 0 to pi by 2, which is 9 times 0 minus minus 1. So it's 9. Therefore, my total flux equals flux over ABC plus flux over CAO plus flux over POA plus flux over POC, PCO. This is 0, this is minus 9, this is 9, this is also 0. So my overall flux is 0. But rather than going through all this computation, we have learned a better way to do this is through divergence theorem. If I simply want to do over a closed surface S, f dot ds is nothing but grad dot f dv, where v is the surface enclosed by the closed surface S. In this particular case, grad dot f is nothing but dou by dou x of y plus dou by dou y of minus x plus dou by dou z of 0. It's nothing but 0 Therefore, my volume integral of grad dot f over dv is nothing but 0, which is also my net outward flux to the enclosing surfaces. So like if we, this is the great advantage of using the divergence theorem. Like in this case, simply in 3 steps we got the answer. Otherwise, this whole thing took a lot of time. And it has applications. The simplest one that springs to my mind is, suppose you have a particle with a positively charged electric field. It will have an electric field which is radiating outwards like this. If I take some surface, some closed surface enclosing this particular charge, and calculate the flux of this electric field over this surface. This is my surface S, and the volume inside is volume V. It's nothing but calculating this particular, using this divergence theorem, we can calculate if there is a net inflow or outflow of the electric field through this closed surface. If there is a net outflow, we can conclude that the overall surface contains, like the volume enclosed by the overall surface S, which is the volume V, will enclose a positive charge. Exactly opposite case happens if you have a negative charge. It's a powerful principle which is commonly used in electrostatics. The sixth problem of the day. So this time I won't go around it the entire way, but we want to calculate flux of this field in this particular octant. We are giving x square plus y square equal to z square. And so this becomes our first octant. And a vector field is f equal to z k hat. Now we want to calculate f dot flux, which is nothing but f dot n ds. Right? But we know from divergence theorem this is also equal to grad dot f dv. In this particular case, grad dot f is nothing but no component of x, component of y, this go to 0, dou z by dou z, which goes to 1. So my flux is nothing but integral over volume v 1 times dv, which is integral over volume v. This is an octant, so 1/8 of the volume of sphere. Volume of the sphere is 4 by 3 pi into r cube. Just move this, end up with pi by 6 a cube. So very simple. If you want, we could calculate this on each of the individual surfaces, and right away we can make a few remarks. The first remark is, I'll again label these A, B, and C. If I look at AOB, my normal vector is j hat, so my flux f dot n hat is 0, which means my flux is 0. If I look at Similarly, if I look at AOC, my normal vector is I hat minus I hat, and again my flux will be 0. If I look at the third one, which is COB, my normal vector is minus k hat. Therefore, f dot n is nothing but minus z, but z is 0 on this particular surface. Therefore, my flux is also 0. So, AOC, so like the quadrants of a circle, AOC, COB, and AOB do not contribute anything to the flux. Only this spherical portion, which is ABC, that will contribute, and the flux turns out to be pi by 6 AQ. Problem number 7. Using the surface integral in Stokes theorem, calculate circulation of the field, vector field F, which is given by x square I hat plus 2x j hat plus z square k hat around the ellipse C, which is given by 4 times x square plus y square equal to 4. If I draw this ellipse, it would look like this. And it is viewed from above. This is my origin. How the path C is, it will intersect y at 2 and minus 2 and x axis at 1 and minus 1. So the statement of Stokes theorem is circulation of f dot dr is nothing but all of f dot nds over the surface S. So for this particular case, we will take the simplest surface, which would be the ellipse itself. And since it's in the counterclockwise direction or surface S, it's the ellipse itself, ellipse bounded by C. And to get the direction, n hat in this particular case is k hat, because so for in this case it's simple that it's a counterclockwise rotating path. But if you remember how it was taught, then we basically, the path is such that, or the normal is such that uh, if we move along the path with, if my outward normal, if my normal is coming out of the page and if I move along the path, then the region bounded by the surfaces has to come to my left hand side. So this is my normal. On the other side, if we take minus k hat as the normal, you will see that if you move along the path shown by the direction curve, that curve C, then the region would fall on your right hand side if n is k hat minus k hat. So for our case, curl of f is nothing but ijk dou by dou x dou by dou y dou by dou z x square 2x z square. Since in our case n is nothing but k hat, we are actually only interested in the k hat component. I'll just write this whole thing down. Dou by dou x of 2x is 2. Dou by dou y of x square is 0. Plus j hat times dou by dou z of x square is 0. Dou by dou x of z square is 0. Plus k hat times dou by, oh, this should be k hat, sorry. This rotate. by dou f z square is 0. So curl of f dot k is nothing but 2, and curl of f dot n is 2 k hat dot k hat, which is 2. Therefore, my line integral for the curve C is nothing but twice of area of the surfaces, which is twice of area of ellipse, twice of pi times half of major axis, which is 2, half of minor axis, which is 1. It should be 4 pi. The first option itself. Next, we have the 8 problem 8, again one on Stokes theorem. So we are given that f is 2y I hat is 3x j hat minus z square k hat, and the circle C is now the binding curve. So nice C given by x square plus y square equal to 3 equal to 9, counterclockwise when viewed from above. Again the same arguments as earlier one, except in place of ellipse we have a circle. So my normal is k hat. If I do curl of f, it's nothing but dou by dou x of dou by dou y of minus z square. Curl of f is ijk dou by dou x 2y 3x minus z square dou by dou y dou by dou z minus dou by dou z of 3x plus j hat times dou by dou z of 2y minus dou by dou x of minus z square plus k hat times dou by dou x of 3x minus dou by dou y of 2y. The curl of f is nothing but this goes to 0, this goes to 0. So k hat times 3 minus 2, which is nothing but k hat. Curl of f dot n hat is nothing but k hat dot k hat, which is 1. Therefore, my path integral is nothing but integral of 1 ds, which is nothing but area of this enclosing region, enclosing surface, is nothing but pi times 3 square, 9 pi. Hope this is clear. Next, we move to the problem number 9. Now we have been asked to use the divergence theorem to find outward flux of F across the boundary of the region D. So from I'll first draw out our D. It's essentially a cube bounded by x equal to plus minus 1, y equal to plus minus 1, z equal to plus minus 1. it would look something like like this. So this is say plain x equal to 1, this is x equal to minus 1, z equal to 1, z equal to minus 1, y equal to 1, y equal to minus 1. And if you want to calculate flux dot n ds over the surfaces is nothing but volume integral of gradient of f over the entire volume V. In this particular case, we can see that grad dot f is nothing but dou by dou x of y minus x, this dou by dou y of z minus y plus dou by dou z of y minus x, which is equal to minus 1 plus 0 minus 2, and therefore my flux is nothing but integral of minus 2 times dV over the volume V, which is minus 2 times volume of this particular cube. Volume of the cube is s cube with s equal to 2. The overall answer should be minus 16. Option B. And finally, this is the last problem for the day. You have to use the divergence theorem to find out outward flux of this particular vector field, capital F, across the boundary of the region D. Uh, cut from the first octant by the planes x equal to 1, z equal to 1. So you got x, you got y, you got z. This is our first octant. This is how it would look like. And we want to calculate the outward flux of F. Okay. Again, we use the divergence theorem. Let us denote the surface F dot n ds for the entire surface is nothing but grad dot f dv over the entire volume V, which is enclosed, whose boundary is the surfaces. Nothing but. Now, first we'll calculate grad dot f, and f is x square I hat plus y square j hat plus z square k hat. If you calculate divergence of f, it is nothing but 2x plus 2y plus 2z. Therefore, my flux is equal to integral of 2x plus 2y plus 2z done over x, y, and z. X will vary from 0 to 1, y will vary from 0 to 1, z will also vary from 0 to 1. My first integration would give me x square by 2 plus x square by 2 plus 2yx plus 2zx bounded by 0 and 1, x equaling 0 and 1, dy dz, which if I substitute x equal to 0 and x equal to 1 is nothing but 1 by 2, sorry, this should be x square, 1 plus 2y plus 2z minus 0 dy dz. Again, this becomes integral of y plus y square plus 2yz dz on between 0 and 1, which if I continue here, it's nothing but 1 plus 1 plus 2z minus 0 again into dz. It's nothing but 2z plus z square bounded between 0 and 1, which is equal to 2 plus 1, 3 minus 0, which is 3. So my overall flux turns out to be 3. That completes the set of problems that I had for this particular week. This completes the problems that I had for this particular week's lecture. If you have any, if you don't have any more doubts, we'll close today's session and see you again next week. Thank you.